I'm sorry, what now?
A quick test question on page 2 or 2.
Yeah, can I just look at it there? The moment of inertia for this? Sorry. So you'll likely have one of these. You will have one, actually. In that particular question, you had 4 balls like this. They were on the vertices of a square, and so this distance is 1 meter, and this distance is 1 meter. They were connected. And then the axis of rotation was like that. And you just want to find the moment of inertia. Now, each of these is 1 kilogram, and the moment of inertia, I, is equal to the sum of mr squared. The reason I know to use this as opposed to using the different shapes, like you have the spheres and the bars and all that, one thing that should key you off is I don't give the radii of these spheres. I just consider them to be little point sources of mass. So that should be one thing that'll key you off, that we're not looking at a regular shape, because I don't give any of the dimensions, and you need the dimensions to find the moment of inertia. So when I want to find the moment of inertia, I just say the sum of 1 kilogram times the r, that's the distance from the object to the axis of rotation, and that's 0.5 meters. So 1 kilogram times 0.5 meters squared plus 1 kilogram, 0.5 meters squared plus 1 kilogram, 5 meters squared, blah, 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 4 times, because there are 4 particles, so I'm just going to multiply by 4. That's 1 times a quarter, which is a quarter, so 1 kilogram meter squared. If you look back at some of the old exams, you can see different types, so different configurations. Like I think one time I gave one that looked, what was it? I don't know, maybe something like this, where I have 3 particles that are on the vertices of a triangle, like that. Say it's an equilateral triangle, 1 meter, 1 meter, 1 meter. One time I think I did the axis of rotation along this way, and in this case both of these particles do not contribute to the moment of inertia, because for both of those r equals 0. Remember, r is the distance from the particle to the axis of rotation, and there r equals 0. And so really what I want to know is, what is this distance? All right? And then this is my r. If I look at this, I have a triangle here, a right triangle. I'm going to draw that over here, where I have a 1 meter hypotenuse and a 1/2 meter, and then this is r. And then you can solve that for r, find out what r is. I won't do that here. It's Pythagorean theorem. Did that answer your question?
Yeah, it's just like kind of like equation to use for when you find the shape of the object. Like I get confused if it's like a cylinder or.
Okay. Okay. So in that case, they were discrete particles because I didn't give the dimensions. There were only a few shapes, and so we have the cylinder. A cylinder is also a disk. So some objects that are cylinders or disks include, for example, like on previous questions, a merry-go-round is a disk. Flywheel, that's like a big gear in an engine. A flywheel is a disk. Anything that's round and solid in the middle is a disk or a cylinder. A sphere, well, a solid sphere, I don't know, what would be a solid sphere? It would have to probably like a solid piece of spherical.
Like would a person be a cylinder as well?
You could treat a person as a cylinder, and in fact, in the past, I've given problems where you have to estimate the moment of inertia for certain things. I think one time I did like a figure skater, and a figure skater you can consider to be a cylinder, just as a rough estimate. A cylinder that is 2 meters tall by about 0.2 meters in radius. You're not going to have any estimations, but yeah, you could treat a person as a cylinder too, as a good first rough estimate.
You said there was one question in the brain how the person attaches onto.
Right. Mm-hmm.
Why wouldn't you treat the person as a cylinder, or is that treated?
Right. Okay, so in that problem, that's a good question. So I have a merry-go-round. This is my merry-go-round. It's rotating about in this direction. And you had to find the moment of inertia of that merry-go-round. You treated it like a disk. So the moment of inertia of this was 1/2 mr squared. That's the moment of inertia of a cylinder. And then you had a little kid jump onto the side of it. And so you have this kid, and he comes, and he jumps onto the side of the disk. A couple things that should key you off here is, first of all, the kid isn't rotating about any axis that we had in our table. So when we have our table, we had two cylinders, right? We had a cylinder that rotates about this axis, and then we had a cylinder that rotates about this axis. And the kid in this case isn't either one of those, right? The kid is actually orbiting around this point. Right? He's not rotating about any axis that goes through his body. Instead, he's rotating about this point of origin that is the merry-go-round. And also, we just make this approximation that the kid is not really a shape, that he's just a particle on the edge. But what should key you off there is I don't give you any radii or any of that type of information about the kid in that case.
There's a question right here, and it's about like using sine or the sine of 60 or 30, whatever you're...
Right. Okay. That's not going to come up. If I give you a force at an angle, it'll just be the angle that you use. But let me explain anyway. If I have a bar and I have a force acting, my torque is Fr sine theta. Right? And that angle theta is the angle between the force and the moment arm. So this is my force, and then we call this direction our moment arm. R is actually a vector, and so it has a direction, and in this case the angle theta is the angle between F and R. Now that is not, however, this angle. So this angle, which I'll call phi or whatever, is not the same as theta. So if I gave you the angle phi, like in the homework, then you would have to take 90 minus phi in order to get theta. So theta, the angle that's adjacent to the moment arm. Don't need to worry about that for the exam, though, coming up. But all the angles that I give you will be measured as adjacent to the moment arm. But it might be important for later, like if you're doing the MCAT or whatever. Okay?
Can you explain the manometer? How does it work?
Sure. Yeah, the manometer is a comparison between one known and one unknown pressure. You can see a couple different problems in this. First of all, let's say that I have a situation that looks like this. This is all filled with some fluid or some liquid. I have a pressure that is acting over here, P, and a pressure over here, which I know, P naught. Now I know that P is equal to P naught plus or minus rho GH. Right? The plus or minus comes about because P can either be bigger or smaller than P naught. So you could have a question, and I have questions like this in some of the old tests, where just asking you to compare P and P naught. So is P bigger than P naught, or is P smaller than P naught? In this, Right, in this scenario, P is bigger than P naught, right? Because I have this force, this bigger force is pushing this liquid down into the column and pushing it up over on this side. So the bigger force is always the one that's pushing the fluid down more. So manometer compares these two pressures, and it takes the difference in the levels of the fluid, which is H, and you can calculate then what is the pressure by that column of fluid H. So in this case, our pressure would be P equal P naught plus rho GH, where rho is the density of the fluid, mercury or whatever it is that you have in your manometer, G is the acceleration due to gravity, and then H is that height of the column. Don't forget your millimeter conversions. Atmospheres are 760 millimeters of mercury. That's where that comes from. It's the height of the column of mercury.
It's like one of the quick test questions. questions, they ask like for CH4, how much pressure does the methane have? So you just work out the same thing.
Right. So in that one, let's see, I can see it from over here. The methane was in the bulb, right? Yeah, so it looks something like this. You had a methane bulb, a bulb. All right. So this is CH4. You have a liquid right here, whatever this is, mercury or whatever. And then you have a difference in height for the two liquids, H. All right, this is P naught. This is was this 1 atmosphere? Yeah, so this was open to the atmosphere. So 1 atmosphere. Don't forget your conversion. This is on your equation sheet, but be careful because atmospheres isn't the SI unit. So anytime you're doing pressure measurements, you'll need to convert that to SI units, which is 1 times 10 to the 5th pascals. In general, it's always safe to convert to SI units. Sometimes you don't have to, and it might make it a little easier if you know when those times are, but it's always safe to convert them to SI units. Just make sure that when you go into the answer on the multiple choice that you still have the same units, because sometimes those aren't SI units. So anyway, P naught is there. This is P, and then, excuse me, that's just P, not P naught. P here is bigger than P naught, so P is equal to P naught, not minus, but plus rho GH. Is that clear?
It says right here that pH is the P pressure of methane is greater than 118.
Right. Yes. What? Yeah, it should be. It should be greater than 1 atmosphere. Yeah, it should be greater than 1 atmosphere. Because if I have one, she said that this pressure here should be greater than 1 atmosphere, because my pressure over here is 1 atmosphere. In order to push this column up, this pressure has to be larger than this pressure. So P is larger than 1 atmosphere.
Does it matter where the liquid levels off at, or?
It does matter, yeah. So if I had a different scenario, say for example, instead, my liquid was like this, and this distance was H, the pressure of my CH4, which is in that bulb, my methane gas, would be less than 1 atmosphere. It would be P naught minus rho GH. You follow me on that? I'm sorry, whatever. Oh, a different liquid?
Yeah, liquid.
Oh, I see. Yeah. I was just looking at upside down. Okay. All right. You will have 1 or 2 pressure measurements questions. Basically, one or two of everything from Chapter 9. All right. What else? That was all for you? Okay. Yeah, Jessica.
Do you know if it's just P and
Okay, P is, or P naught, this is our known pressure, and this is our unknown.
So whichever one we do.
Right, yeah. Whichever one is. Bye, you guys. Have a good day. Yes. Right. The one that I give you will be the known pressure.
Yeah,
P naught.
on this one it says pressure acts on the left side, so you know that one.
Yeah, whatever one I give you. Yeah. All right. Is that clear? Okay. Good questions. Can I just sort of go quickly and summarize all the major topics? Is that okay? I know y'all saw that this morning, but it might be useful again. And then we'll look at Chapter 8 in more detail. Okay, like all the different questions that you could see in Chapter 8. All right. So, Chapter 7. We had kinematics. All right, you can think of this in 2 tiers, sort of calculations that you might do. All right, you had those 2 equations, theta equals omega naught t, 1/2 alpha t squared. Several problems that we worked in class, in the quick test and in the old test, where you have to find different values, either theta, omega, or alpha. So you'll have 1 or 2 questions just doing calculations like that. And then also conceptual or sort of relationships. And that is, how is theta related to t? How is omega related to t? Well, theta is actually related to t squared, so changes in time cause a square in those changes in theta. So we had several questions like, for example, if theta is certain value after time t, what is it that after 2t? Then it would be 4 theta. John?
Would you have equations where we have to put an equation inside another equation?
No, there will be no
So
systems of equations.
So
Right?
there'd be none like that like that on homework.
There was one in the homework, right, that had where you had to substitute one equation into another, and you won't have to do any of that. Huh? It was the dentist drill one, right? And you won't have to do that. We've done that before, but not on this test. Okay. So the conceptual questions would be something like what we've seen before, where like I said, if theta is blah over time t, then what is it over time 2t or half t or quarter t or whatever, all right? And then after that we had shoot, what was the next thing? I'll write this down. I'm sorry, I just came a blank. It's a rough week for y'all, huh? Is it a rough week? Yeah, me too.
Relationships.
Yeah, that was this conceptual, so that was this. Was it just centripetal forces?
4, you put FC is equal to mv squared over r.
Okay, yeah, so centripetal force. Okay, and these are the forces that cause circular motion. We can apply Newton's second law. We can say that the sum of the forces here is equal to ma. All right, that's always true. And when we have something that's moving in a circular path, say a ball on a string, for example, and it's moving in this circular path, it is accelerating. If it has a constant speed, remember the velocity is always changing because it's always changing direction, so we have to describe its acceleration. All right, so even though it's moving at a constant speed, it has an acceleration, and we describe that acceleration as v squared over r. It's called the centripetal acceleration, which we call AC. And then the centripetal force then we call FC, which is just mv squared over r. That comes up in several cases. For example, we did work a problem, and you saw this in the homework and on the test and what have you, of a car going around the corner. This is a part of a circular path that has a radius r, and the forces acting there are the centripetal forces, or excuse me, the only force that's acting here between the car and the road is the static frictional force. And so we can write Newton's second law, say the sum of the forces equals MAR, or MAC rather. The sum of the forces is just the static frictional force. That's equal to mv squared over r. And then we can, in those questions, if you recall, yeah, John?
How come it's F static instead of kinetic?
Because if you remember from chapter 4, when your wheels are turning, the surface of the tire and the surface of the road don't move with relation to one another. It's only when the wheels lock up do they start to slide with respect to one another, and then that would be kinetic friction. All right. Though you won't have to discern between the two. I'll give you what you need if you have a problem like this.
I was just wondering, like,
I
why.
understand. Here our static friction is mu times the normal force. That's from chapter 4. That's not on the equation sheet, however, so I'm pretty sure you're going to have a problem like this, so make sure that you remember that. 95, I don't remember how to put it on there. I'm pretty sure I did. So that's mu times mg equals mv squared over r. And then we can solve this. My maths cancel. Whatever it is that you're solving for, you might be solving for mu, you might be solving for v, whatever. Let's just solve for v. It turns out it's the square root of mu gr. All right, so that's like the maximum safe speed that you can travel around on these. Right, that's our centripetal force, centripetal acceleration. There are some other problems in the homework and in the notes. You know, as always, you should look through the notes and see sort of what are the various topics. But those are the big broad topics: kinematics, calculations, sort of conceptual, relational questions, and then centripetal forces. Questions on Chapter 7? We can come back and work some problems on the test later. Let's look at Chapter 8. All right, so Chapter 8. There's a lot in Chapter 8. In fact, Chapter 7 will be slightly fewer questions probably than Chapter 8 or 9. So thinking about 6 or 7 questions from Chapter 7, and then that'll leave about 10 each from Chapters 8 and 9. Chapter 8, Moment of Inertia. We had Newton's second law. Torques, energy, and momentum. Those are all the major topics. I'll just summarize them here, and then we'll go back and look at them in more detail. I is the sum of mr squared. We've already done some of those, like for discrete particles. Or also, I can be for a particular shape. Those are on your equation sheet. That's that I, 1/2 mr squared, 1/12 mv squared, whatever. You'll need to be able to discern those different shapes in the problems. Reading the problem and then picking out the shape on the sheet. Torques, the sum of the torques. You'll need to be able to calculate the sum of the torques. And then also torque is equal to Fr sine theta. That's like the bar with all the different forces on it. We can look at one of those. You'll have one of those on your test. And then also when you find that net torque, coming up here for Newton's second law, and we had several examples of this in the homework and on the quick test and what have you, but this is just Newton's second law. Sum of the torques now is equal to I times alpha. And as in those problems, usually you have to find alpha. We have to find the sum of the torques, you have to find the moment of inertia, then you find the angular acceleration, and then from that you find whatever, angular displacement, angular velocity, something along those lines. We can look at one of those in a bit and just sort of go through that. And then energy is, kinetic energy is 1/2 I omega squared. All right. And then also the idea that if you have energy, then you can change that energy, either give an object that energy or take away that energy from an object by doing work on the object. That's the work energy theorem. And then finally, momentum. Angular momentum is equal to the moment of inertia times the angular velocity. Remember before it was P equal mv, but now we're replacing that P with an L. Our mass, or our inertia, is now our moment of inertia, and our velocity before is now our angular velocity. And then the big idea here is that when there are no outside torques, angular momentum is conserved. So Li is equal to Lf. That is that I initial, omega initial, equals I final, omega final. So for example, if you have an object whose moment of inertia goes up, then their angular speed goes down. That's like the figure skater that puts her arms out, increasing her moment of inertia and decreasing her angular speed, her angular velocity. So those are the 5 big topics in Chapter 8. And each of them have, well, those are really just 5 big topics. So you'll probably see a couple questions each on those. All right. Let's break from that and we'll go into the old test and look at some different questions from each of those. Is that okay? All right. Oh, that's not what I want. And then we'll come back to Chapter 9. All right. Okay, so this first problem right here, number 1, this, I have a merry-go-round, radius 1 meter, started from rest by a constant horizontal force applied tangentially, and just find the angular speed. So if we're looking back at this broad categories, that is looking at this type of problem, Newton's second law type problem. But it also involves finding the torques and finding the moment of inertia as well. So it sort of incorporates those 3 broad categories. Excuse me. The first thing that you'll need to do is to find the moment of inertia. I like to write down everything that I know. The mass is 100 kilograms. This is a merry-go-round, so it's a disc, or it's a cylinder. It has a radius of 1 meter. Make sure that you're very careful about reading the questions, because sometimes we give the radius and sometimes we give the diameter. I try to highlight and bold words like that might lead you to get the wrong answer. But for example, if I gave the diameter here, you'd need to take half that. Is that clear? So if you see diameter, you need to take half of it almost always for finding the various values, certainly for the moment of inertia. So what do you do if you get the diameter? Divided by 2. Right. So don't forget that. Be careful when you're reading, because sometimes you can read through them quickly and just miss that. All right. So let's go ahead and find our moment of inertia. For a disk, you would look on your equation sheet and find that it's 1/2 mr squared. So that's 1/2 of 100 times 1 meter squared. So that's 50 kilogram meter squared. All right, so that's my moment of inertia. And then I would also want to find the torque. Let's see. The force is 50 newtons applied tangentially to the merry-go-round. So I have a force equal to 50 newtons. And it's applied tangentially. So I have this merry-go-round. Looks like this. My force is applied there. The radius then is 1 meter. So my torque is F times R, just 50 newtons times 1 meter, or 50 newton meters. So I have this torque acting. That's one step. This is my I. Now next, I'll find the alpha. Alpha is equal to torque over the moment of inertia. That's going to be 50 newton meters over 50 kilogram meters squared. So I is 1 radian per second squared. Okay, and then finally, lots of steps here. The last step is I want to know the angular speed. That's omega naught plus alpha t. That's going to be 0 because it starts from rest. Alpha is 1 radian per second squared. T is 3 seconds, so I'm looking at 3 radians per second. There's a lot of steps in that, but the question won't be much deviated from this. It might be a different shape, like it could be a sphere, or it could be a bar, or it could be something along those lines, but you'll have the same steps throughout. So you will have a question like this. It might not be a disk, it might be something different, but it'll be very similar to this, where you have a net torque acting on an object, and you need to find its moment of inertia, you need to find its angular acceleration, and then you need to find either the angular velocity or the angular displacement. If instead I asked for the angular displacement here, I would just say theta equals 1/2 alpha t squared. That would be 1/2 of 1 times 3 seconds squared, which is 4.5 radians. So you will have one like that. Y'all could do that right now? Just following those steps. It'll be very... Which one is this one? Well, this... Oh, this is the angular displacement. I didn't ask that in this question, but I could ask that. Like I said, this brings everything together. It brings together moment of inertia, net torques, Newton's second law, and kinematics. So lots of steps. I don't usually like having questions with that many steps, but just be prepared for it. It
So
will.
from there, we can assume that it starts from rest.
It'll always start from rest.
Okay, so it'll start from rest.
It says it right here, but yeah, you'll want to look for that language. But yeah, it'll start from rest. Okay, so that's 2.5 points down, right? Or however many. How many points are they? No, they're almost 4 points, right? 3.5 points. Okay. I clear that. Is this helpful for you? Yeah. Okay. So that's one type. This is, huh?
What test is from?
Oh, this is Fall 09, Exam 3. These are all on the internet. So this one is an energy problem. Nothing terribly complicated about these. You might have to find the moment of inertia, but otherwise they're pretty routine. You just have to know what is the equation for energy. That's 1/2 I omega squared. In this case, it's a thin hoop, and the moment of inertia for a hoop is in your equation sheet. It's just mr squared. That's going to be 1/2 kilogram times 1 meter squared. So that's 0.5. So I just do 1/2 of I, which is 0.5, times omega, which is 10 radians per second. And then that's squared. And just how much energy does that contain? Well, 1/2 of 1/2 is 1/4, times 100 is 25. All right, so that should be an easy 3.5 points. It's just really, you have to find the moment of inertia, and then using the right formula to find the kinetic energy. I could rephrase this slightly. I could say how much work is required to either stop the hoop, or how much work is required to get the hoop up to the same speed. And it's the same set, right? The work and the energy are the same. That's the work energy theorem. Work is equal to change in energy. So,
Maybe on the last thing for us, change the work and kinetic energy.
right, yeah, work and energy are the same. All right. So in those broad categories, that falls right here. And you still have to know the moment of inertia and be able to find that, but energy is the larger thing. Okay? You'll need to know how to find our net torque when I have multiple forces acting. So we did that previously in number 1, but you also need to be able to, given a, let's see, do I have one here? Let me go back to another test. See, this is Fall 11 exam. See if I have one here. Okay, yeah, so something like this, where you have an object with multiple forces, you need to find the net torque on something like this. You will see something like this. Not many, I don't want any surprises. Everything's going to be pretty much straightforward. But there's a lot of stuff, so that's why, because there's just a lot of material. So if I want to find my net torque, you first identify what is your axis of rotation. It's about point C. And then you identify the forces that cause torques. So I'll call this torque 1, I'll call this torque 2, and I'll call this torque 3. If there is a force acting here, the torque due to that force would be 0. Because remember, torque is equal to FR sine theta. And if R equals 0, as it does for this one, R is the distance from the axis of rotation to where the force is applied. And when R equals 0, then that torque is equal to 0. So that doesn't provide any torque. That would be like trying to open the door by pushing on the hinge.
T3 is 0, right?
Okay, we're going to get to that, yeah. So this one is 0, and T3 is also 0 because of the sine theta term, right? Because theta is equal to 180, and so that sine of 180 is equal to 0. This is like trying to open the door by pushing into the door instead of pushing perpendicular to the door. All right, so both of those forces, this torque 4 I'll call it, which isn't on the problem, and torque 3 both provide no torque at all. Those forces provide no torque. So really we're just dealing with torque 1 and torque 2. And then you want to identify, are these positive or negative torques? And I like to take a pen. I put it so that it rotates about there. And then I imagine, what if I pull up? Then this object will rotate in this direction, and that's counterclockwise. So this force causes a counterclockwise rotation, which is positive. And this force causes it to rotate in this direction, and that's a clockwise rotation, which is negative. So this force causes a negative torque, and this force causes a positive torque. All right, what was torque 2? I forget. Positive?
Yes.
Yeah. And torque 1 was negative. Okay, so that's the next step, is determining which ones are positive or negative torques. And then you just want to calculate the magnitudes of the torque. So torque 2 is 25 newtons times this distance, which is 1 meter. I know it's 1 meter because this is 2 meters and this is 1 meter, so this has to be 1 meter as well. All right? And the sine of 90 degrees is equal to 1. So if your force is perpendicular, you can just leave off that sine theta term. And so this is 25 newton meters, and it's positive. And torque 1 is equal to negative 12 newtons, 2 meters, cosine of 30. I'm sorry, sine of 30. Oh yeah, so that's negative 12 newton meters. All right, and then you just add them up. So the sum of the torques is torque 1 plus torque 2. That's negative 12 plus 25, which is 12 or 13 newton meters. Oh wait, no, that's not right. I have a mistake here somewhere. Oh, yeah, I'm sorry. Up here I made a mistake. This should not be 2 meters, but 1 meter. All right, because the distance from this point to right is 1 meter. You're right. Yeah, 1 meter on each. So I had it right over here, but not over here. So that gives me negative 12 times a half, which is negative 6. So here we get negative 6 plus 25, which is 19. And it comes out positive, so we know that it's counterclockwise. This is equal to positive 19. That means it's counterclockwise. You will have a problem like this. You have multiple forces. You have to find the net torque.
Is it the sine because it's in the y direction?
The reason why it's sine? Well, the sine comes about because you want the component of the force that's perpendicular to the moment arm. So yeah, what you're saying is correct, that you want the force in the y direction. But it's always sine, right? So that's just the definition of our torque, that it's FR sine theta. It actually goes back to something we call the cross product, which you probably won't get to it. You do it in Calc 3, which I don't take. But that's where it comes from. But the idea is the same as what you said, that you want the force that's perpendicular to the moment arm. All right?
You just didn't include the sine now because it was 1, right?
I didn't use the sine over here for torque 2, right, because it was a 90-degree angle, and the sine of 90 is 1. If that confuses you, just always use the sine term. Just make sure, when you do sine of 90, then it is equal to 1. And the sine of 180 is equal to 0, or 0. Sine of 0 is 0. All right, so in those broad categories, that is this problem, finding the net torque. And you will have a separate problem where you have to find the net torque. Okay? The last broad category is this momentum. You only have something like this. Now you could have I'm pretty sure you have a conceptual question that asks, you change your moment of inertia, what happens to your velocity? If you increase your moment of inertia, you decrease your velocity. If If you decrease your moment of inertia, you increase your velocity. So that's like the figure skater. Figure skater puts her arms out, that increases her moment of inertia, which decreases her speed. And when she pulls her arms in, she's bringing more of that mass to small radii, which decreases her moment of inertia and increases her speed. She speeds up in her spin. All right. As I said in class today as well, I would expect a problem where I have two objects that are spinning that come together. Or let's say I have one object. I did a similar example in class today. Let's say I have a wheel that's spinning. It has a radius equal to 1 meter, and it's spinning in this direction with an omega equal to, I don't know, 4 revolutions per second. And it has a mass equal to 10 kilograms. It's spinning, all right, spinning along an axis that goes through here. So imagine that's like a shaft that it's spinning upon. And then let's say that I have something else. I don't know, a bar, for example. I have a bar that has a length equal to 2 meters and a mass equal to 10 kilograms. And it's initially at rest. So initially it's not spinning at all. And it's not uncommon when you're designing big systems or big engines or motors that you bring these two together and then they spin now at a different rate. So I have two objects that are on a shaft and then I engage them somehow through gears or whatever. And then I want to know what is the new speed at which this system is spinning. We've worked problems similar to this. If you remember, there was a quick test about the kid jumping onto the merry-go-round. When the kid jumps on the merry-go-round, he changes the moment of inertia. Well, a similar thing here. When I bring the bar and the disc together, I change the moment of inertia. So the first thing you want to do here is just calculate the moment of inertia. So first, for the disc, I is equal to 1/2 mr squared. You would look at your table, and the moment of inertia for a disk is equal to 1/2 mr squared. And so that's going to be 1/2 of m, which is 10 times 1 squared, or 5 kilogram meter squared. So that's my moment of inertia. And then over here, my moment of inertia, I, is equal to 1/12 mb squared. M is 10. B is 2 meters. This is also from your table. I think it's called a thin rod or a bar or something. I forget what it's called. A rod, okay. And so that's 1/12 of 10 times 4 is 40. So that's 40 over 12, 20 over 6, 10 over 3 kilogram meter squared. Okay, so my moment of inertia initially is equal to just 5. That's this moment of inertia, because that's the only thing that's spinning at first. But then when I bring the bar in, this is initial, I final is going to equal to 5 plus 10/3, which is 8.3. That's my new moment of inertia. So I've now increased my moment of inertia. Y'all with me on this? Yeah?
So I think if you just add them together.
You add them together, right. Yeah, it's just like the kid on the merry-go-round, except now instead of having a discrete particle, you're adding a separate shape. You're engaging them so they spin at the same rate, and so now they're going to spin at a new rate. mr squared. But same idea here. You with me?
This we just need a special equation.
Right. The only difference is you look on that table to find what is the moment of inertia of a bar or a rod or whatever it is. Okay, and now we can say Li equals Lf, I initial, omega initial, equals I final, omega final. I initial is 5, omega initial was 4, I final is 8.3, omega final, I solve for that. That's going to be 20 over 8.3.
So this one stays in revolutions.
Right, you can keep it, you don't have to do the units on this. If you want to change it to radians, that's fine, and you'll never go wrong, but let your units for the multiple choice answers sort of guide you. Like whatever the multiple choice answers are in, you should just go and convert all your units to that. I don't think I have many problems where you have to convert units, except for those that are explicitly convert the units of this, which you'll also have. That'll be a good guide for you, yeah. But you never go wrong with converting to SI units. Just make sure that your final units are the same as what's offered. And 20 over 8.3, yeah, that's about 2 point something. I don't know what that is. 2.5, I guess, roughly. Okay, 2.4. All right. That's all the major categories of questions for Chapter 8. You'll also want to go through the conceptual test. We sort of dealt with some of those here, but dealing with, momentum is a big one. We already talked about that, sort of conceptually what happens, and then also the moment of inertia questions. So we had some questions in the quick test that had you rank moment of inertia for certain things, being able to do that. What is the moment of inertia for different shapes? And in those, you're looking particularly for which of these has the most mass at large radii. So, I don't know, something like this. Let's say that we had a rod that can rotate about several axes. Let's see, it can rotate about that axis, or that axis. A, B, or C. Which of those would have the larger moment of inertia, A, B, or C? When moment of inertia, the largest you're looking for is where more of the mass is at large radii. So which axis rotating about those, either axis A, B, or C, would have the larger moment of inertia? Let's see, what do you think? What do you think? All right, well, which axis is not C? But it is A, because for A, more of the mass is located at larger radii. See, if I'm rotating this thing about an axis A, if I'm rotating about this axis, I have mass all along here, and I have mass out at the furthest radii that it can be. And so this is harder to spin. It has a bigger moment of inertia than something like this, where I have mass at smaller radii. I can see this distance is smaller. And that I is mr squared. That r carries a lot of weight because it's squared. So something like this, my moment of inertia would be larger about axis A than either B or C, because that r value would be bigger. I have more mass at larger radii. Okay? So follow me?
That would give it a bigger inertia.
Yeah, axis A gives a bigger moment of inertia. Similar idea, right? We talked about this in the notes, but it's easier for me to spin about this axis than it is to spin about this axis. For a similar reason here, I have mass just out to like this radii, but when I spin about this axis, I have mass at much larger radii. So it's a lot more difficult to do a cart.
Is that the same concept as ballerina with her arms out? She's larger moment of inertia when her arms are out as opposed to...
Yeah, because when she puts her arms out, she's extending mass out to larger radii. And so, since that r is squared, it increases her moment of inertia by a lot. That's why she can change her speed so drastically. Okay, that's Chapter 8. Any questions, particular questions? All right, that's probably a pretty good summary. I would go through the concept test as well, though. I always find that's a good guide. And the homework and the old test. All right, let's look at the broad categories in Chapter 9. Gosh, there were like 6, 7, 8 categories in Chapter 9. I would expect about 1, sometimes 2 questions from each category, but probably just 1. All right, we had density, just definition of density. The mass of something is this, the volume of something is this, what's its density? Or the density is blah, what's its mass or what's its volume? All right, you have that table for density, so you might not have the density in the problem, but it is on your equation sheet. So the density of all the common things is on that table. Also, we had just sort of matter in general, the states of matter, solids, liquids, gases, plasmas or ionized gases, Solids are generally more dense than liquids and gases, although not, of course, for water, right, where the solid ice is less dense than water. But certainly in solids, the structure is set, whereas in fluids, the molecules move with respect to one another. Also, fluids include what and what? Gases and liquids. So remember, fluids is just a general term for anything that flows. Plasma's also a fluid, I guess, yeah, because it's a gas, right? It's just an ionized gas. We don't need to think of it as a fluid because you don't really use plasmas that much, but yeah, it's a fluid. Okay, so matter. One question maybe. Let's see, density, matter, pressure. Now in pressure we had several subtopics. We had pressure at a depth. So that is, I'm submerged in water. Say I'm at this point down here, I'm a certain depth, h. Let's say that I have a certain pressure at the top here, P naught, and I just want to know the pressure here. That pressure is equal to P naught plus rho GH. I can think of it as a column of liquid sits on top of that point, pressing down onto it and causes that pressure to occur. And then I also have this additional pressure, P naught, pushing down on it. So this term represents the pressure due to that column, and then this term represents the atmospheric pressure, or that additional pressure due to the atmosphere pushing down on the top of the surface of the liquid. So you have pressure at a depth, you have pressure measurements. Right. Measurements, manometer. We can look at some of those, but it's like the ones that we worked before. You could have both calculations, where you say P equals P naught plus or minus rho GH. But of course, having to figure out, do I use plus or do I use minus here? And like I said, that was like the problems that I worked earlier when Sarah was here and she asked about. You could also just have conceptual problems where I ask which pressure is greater, right? I give you a picture like this. I have one pressure here. I have one pressure here. We'll call this P1, call this P2. Which pressure is greater, P1 or P2? In this case, it would be P2, right? Because the level of the liquid is down lower than the level here. And so
if we were trying to find the pressure at P2 would just be the P naught plus P2.
Right. P2 would equal to P1 plus rho GH. But if it were switched, P1, for example, would equal P2 minus rho GH, because we know it's less, huh?
Because it's less.
Right, because it's less. So you have pressure measurements using a manometer or a barometer. A barometer, remember, is just a special case where P naught equals 0. So I'll list, if you have a barometer, I'll call it a barometer, and I'll also say that this pressure inside the barometer is equal to 0. So it should be clear that it's a barometer. And then also just general pressure. So pressure is force over area. So not necessarily dealing with liquids or fluids, but just dealing with, I strike a force, I have a force acting over a certain area, what is the pressure? You had a homework question. Was it the chisel? Did you have a chisel question? I don't remember, but just what is the pressure given a force and area? Pressure is force over area. So several categories in pressure. That's it. Right, like in the concept test, yes. So, for example, like the ice question, which we often find ourselves in, walking out on lakes that are frozen over, they start to crack, right? You want to increase that area as much as possible, okay? Which, if you increase the area, that decreases the pressure, even though you're still applying the same force. Okay, so pressure, then we had several categories. Pascal's principle is also dealing with pressure. Pascal's principle says that if I apply a pressure onto a fluid, P, I apply a change in pressure, then that change in pressure is felt at every point through the fluid. All right, so I feel a delta P here, I feel a delta P here, delta P here. I also feel that delta P on the sides of the container. So anytime I have a pressure that's applied to a change in pressure on a fluid, a liquid actually, an incompressible fluid, then I feel that same change in pressure. If it's incompressible, that should be sort of intuitive. An incompressible fluid means that you just can't change its shape. And so if I apply a force anywhere on it, I'll feel that same pressure all the way throughout. So you could have just sort of a conceptual problem based on that, but also the big idea here is Pascal's principle, and you will have a hydraulic lift type problem, or a hydraulics problem, where if I put in a pressure here, P in, I get out a pressure here, P out.
Is that why you have air bubbles in the hydraulic system? We leave it out because air can be compressed.
Air is compressible, right? And so when you put in a force, it doesn't cause the output force to come, but instead it compresses those air bubbles. That's exactly right. It's also like in your, I have this probably more, but like you have air in your brake lines, your brake pedal feels really spongy because you aren't pushing the brake pads, you're instead just compressing that air. But you don't really have that problem anymore. So here P in is equal to P out. That is F in over A in is equal to F out over A out. You have a homework problem, several questions. You're going to have just a basic hydraulics question. Given an input force on an input area piston, what is the output force with the output area piston? Given. Okay? Y'all can do that? Should be pretty basic. Pascal's the formula for that is on the equation sheet. I think it is. Let me take a double look.
It works because for the left side, you're putting in a greater amount of displacement.
That's right.
So the force is larger on the other side, but at least put a small amount of displacement.
That's right. But your conservation of energy still holds. Right. That's not going to be there tomorrow, but or whenever y'all have it. Where is that? Okay, this isn't on the equation sheet actually. The equation for pressure is there, but Pascal's principle is not there explicitly. But Pascal's principle, as I said, is more this idea that a change in pressure carries throughout the fluid. And so if I have a pressure here, I get that same pressure here. So it's really just an application of pressure, but more specifically that P in equals P out. Y'all are okay with that? You need to know the definition of Pascal's principle and then also how to apply it mathematically. Those are on the test. As of now, I haven't edited it down, but as of now, it's on the test. Okay, so we have Pascal's principle. Now, if y'all need to leave, I understand. I'll have to leave in about a half an hour, but yeah, I'm recording it. I'll put it on YouTube this afternoon. All right. What else we have? Archimedes Principle. Oh, and then fluid flow. So just a couple more things. 3 more things. Archimedes Principle. This can get complicated. It'll be pretty simple for your test. Just a couple of things. You need to know what Archimedes Principle is. First of all, it says that the buoyant force equals the weight of the displaced fluid. So if I have an object that's submerged, it displaces a certain amount of fluid. The volume of fluid that it displaces, the volume of the displaced fluid, is equal to the volume of the object. Y'all probably done this in chemistry, measuring volume by displacement. If you have an object, I want to know its volume, I just submerge it in water and measure the change in the volume of the water. And that gives me the volume of the object, which is a nice way to find the volume of irregularly shaped objects. So the displacement volume is equal to the object volume. And so the buoyant force then, I can say, is equal to the weight of the displaced fluid, that's the mass of the displaced fluid, times g. I know that rho equals m over v, so the mass of the displaced fluid is the density of the fluid times the volume of the object, or excuse me, the density of the fluid times the volume of the displaced fluid. That's the mass of the displaced fluid times g. But because of this relationship, this is rho fluid, volume of the object, times g. So that's my buoyant force. Need to know how to calculate the buoyant force and what it's the definition from Archimedes' principle, that it's the weight of this displaced fluid. And then also we have this idea of apparent weight. So if I have an object, it has a certain weight, Fw, but if I have a buoyant force acting on it, then the apparent weight, that is, what weight does it appear to have, will equal to the actual weight minus the buoyant force. So for example, if I weigh 700 newtons, I go in the pool, and there's a buoyant force of 100 newtons acting on me, then I have an apparent weight that's less than 700. I have an apparent weight that's equal to 600 newtons. You understand that concept, apparent weight? The weight that you appear to have when you're in a fluid is just you subtract the buoyant force from your actual weight. Okay, and then the last thing are fluid flow. I'm sorry, is that okay? Can I go from there? Is this okay, y'all? Yeah? Okay. And then the last things are fluid flow. You have two things, equation of continuity. This is just based on the conservation of matter. If I have a pipe, looks like this. I have a certain area down here. This is A1. I have an area down here. This is A2. A2 is obviously smaller than A1. I have a certain flow of fluid, V1, the speed of the fluid going here. I'm going to have a much larger speed down here because all the fluid that comes into this area right here that travels through this section of the pipe, all that fluid has to travel through this smaller section of the pipe. And so if I make it smaller, that means it's going to have to go through there faster in order to get that same amount. And this is encapsulated by this equation, A1 V1 equals A2 V2. All right, so for example, if A2 goes down as it has here, V2 has to go up because this quantity remains constant. The product of those two numbers is always equal. All right, like a garden hose, put your finger over the end, right? You close off that area, it makes it come out faster. So that's the equation of continuity based on the conservation of matter. If I change my area, I change my flow speed. And then the next one is Bernoulli's principle. This is in your equation sheet. It's based on the conservation of energy. You'll know this because the equation sort of looks like our energy things. The equation is this, P, not P equals P plus 1/2 rho V squared. That sort of looks like kinetic energy. It's actually kinetic energy per volume plus rho GH. That looks like gravitational potential energy. This is equal to a constant. This is always constant. Which is what we said with conservation of energy back in chapter 6, I guess, 5, 6. That energy is constant when there are no outside sources of energy. Okay, so honestly, this is always going to not be relevant because our H won't change. All right, so you might have a problem where you have to calculate something where I give you like an initial pressure and a final pressure, and you have to and I give you an initial speed, and you have to find, say, a final speed. All right. Another thing that comes out of this, as we talked about, is that if the velocity goes up, the pressure decreases, and vice versa. If the velocity goes down, the pressure increases. And there were several conceptual questions in the quick test regarding this idea. For example, we had the idea where if you have an artery that becomes clogged, then you have blood flowing through here. Here, your velocity goes up, and so within this blockage, your pressure goes down. Right? So that doesn't mean your blood pressure goes down. Your blood pressure actually systemically increases. But in that isolated location, you get a very low pressure. You can get your collapse of your artery. So that's everything from Chapter 8. Do you want to look at some questions? Yeah, Lathan?
I have a question about 231.
Page 231? It'll take me just a second. Can you go ahead and explain it? What does the question say? I don't.
Oh, I'm sorry. The figure shows a manometer which is filled with mercury and pressure of the atmosphere is 118 impacts on the left side of the manometer. The temperature of the methane gas is out below is 37.
Oh, yeah. Okay. Yeah, just a second. I'll pull it up here. Hey, Kesley. A lot of material in this test. Okay, there is a lot, but like I said, because there are a lot, it's sort of in your favor because the questions will all be familiar to you and fairly routine. I mean, obviously, I'm not using the same questions from previous tests, but they'll be very similar. All right, what was the page number, Lathan?
231.
Something like the one with the-
This quick test right here? The quick test, this one? Yeah. Let's see, what you got? Well, you just didn't really know how to do it? Or,
I got the right answer, but I just...
okay, let's step through it. It's a good question. You will have one like this. Let me erase this.
Try to find the pressure on the right.
I think so. Yeah, what is the pressure of the methane? That's the CH4 gas. The temperature there is given. You don't need the temperature at all. So basically you have two pressures here. You have a pressure here, and you have a pressure here. I'm going to call this P0, because I know that pressure.
Give us the density.
Right. Or I might not give it in the problem, but there is a table that you'll have with densities, and then also the Young's, you'll have a
It'll
table
be provided in some way.
on the equation sheet. I might provide it in the question, but if it's not, it'll be on the table. All right. I want to know the pressure of this methane gas, right? So I know that pressure in a manometer is equal to P0 plus or minus rho GH. So the first thing I want to find is P0 bigger, or excuse me, is P bigger or smaller than the atmospheric pressure? And in this case, because this fluid is pushed down from this area, I know that this pressure is bigger than this pressure. Because I'm pushing down with a bigger force here, forcing the fluid on this side to be pushed up. So I know that this pressure is bigger than this pressure. So when I'm calculating P, I'm not going to use plus or minus sign. I use minus. I say P is equal to P0, which is the bigger of the two pressures, minus this value. And this rho GH is represented by the height of this column. So I would say that P then, which is what I want to know, the pressure of the methane gas, is equal to P0 minus rho GH. And then it's just a matter of putting in the numbers. So you have to be careful because P0 here is 1 atmosphere, but that's not SI units. So you have to convert it to pascals. 1 times 10 to the 5th pascals. You don't have to know that. It is on your equation sheet, but it's a good number just to know. Minus the density, which is 13,600. 10, acceleration due to gravity, times h, which is 5 centimeters. And so you'll need to know how to convert centimeters to meters. That's move it over 2 spaces, 0.05 meters. And so that's 1 times 10 to the 5th minus some value, So the only answer it can be is B here, because I know that P has to be less than P naught. P naught is 100,000, 1 times 10 to the 5th, and it actually turns out to be 93,000 pascals. All right. Does that help a little bit, Lathan? Yeah. What other questions are disturbing you from this chapter? Chapter 8. No.
We go to like conceptual problems.
Mm-hmm. Yeah, let's look at some of the old examples from chapter 9.
Yeah.
So I'm going to have to go in about 10 minutes or so. See, this is chapter 9? Yeah. I do, right? What's tomorrow? Wednesday? So tomorrow, I have office hours at 7. I get in a little before 7, so if you want to come in that early, that's fine. But I also, after 7:30, I come back at 9. So tomorrow, basically, 9 to 11:30, 9 to 11:15, and then like 1 to 3:20. So I don't know what my office hours are, but I'm there those hours. Oh, let's see. All right, so Bernoulli's equation is based on which of these laws? Which is it? Bernoulli's equation? Energy, conservation of energy. Now, if you forget, look on the equation sheet, you'll find Bernoulli's equation. It sort of looks like it has energy. Rho GH, 1/2 rho V squared. It's conservation of energy. Let's see, these are all calculations. Oh, this is an application of Bernoulli's principle. Where is the pressure highest? Actually, both Bernoulli's principle and the equation of continuity. Where is the velocity highest? At points A, B, or C? Right, so I have a small velocity here, bigger velocity, and a bigger velocity here, right? Because that area is getting bigger, and I know that the product of the area times the velocity has to be constant. So as the area gets bigger, or excuse me, as the area gets smaller, the velocity gets bigger. And I also know by Bernoulli's principle that with a small velocity, I have a big pressure. So my pressure actually gets smaller as I go from left to right. So the pressure is highest at where? At point A, right. That's an application of equation of continuity and Bernoulli's principle. That's a good question. You can see something like that for the test. Take this away. Let's see. No dark matter. So none of that business about dark matter. Here's one about the manometer. That's just the relationship between P and P naught. Which one's bigger here, P or P naught? P naught is bigger, right? Because this level of the fluid is lower than this level of the fluid. So this force is bigger than this force. Or that pressure is bigger than that. Right, if you're finding P, you would say P naught minus rho GH, right? If you actually had numbers. You didn't in this problem, but if you did, that's what you would use. That's it. Let's see, we can look at some others if you want. F11. Let's look at this follow 8. Second. All right, here's one, number 11. In a mercury barometer, the height is 760 millimeters. If you have a tube that has a larger diameter, how high will the column of mercury be in this case? Y'all know? If you're in the class, we actually didn't do this in class. Remember, P is dependent upon rho, G, and H. So the pressure is only dependent upon the height of the column of mercury, or vice versa. Only the height is dependent upon the pressure. So if I go to a larger diameter tube, how is that going to affect the height? No, it's the same, right? So it doesn't matter the size of your tube, it's only the height. So nowhere in this equation do you see diameter of the tube or area of the tube. So the area is not or the height of the column is not affected by the diameter of the column.
So it's just the height of the column itself.
Right.
I'm thinking like, say you had like this high, small one.
No, it doesn't do that because it's pressure, which is force over area, and so the area cancels out basically. And so if you make the tube bigger, it still stays the same height. And we're at 12. Not nor 13. You squeeze the end of a garden hose, make the cross-sectional area smaller. What happens to the pressure then of the water? Does it increase, decrease, or stay the same? It decreases. Because you've decreased the area, you increase the velocity, and then by Bernoulli's equation, if you increase the velocity, you decrease the pressure. And then that's it. We get into the next chapter. Okay. Any other questions? Yeah, I'm kind of inclined to stop there if that's okay. If y'all have particular questions, I'll go over them. But no. All right, I'm going to post this to YouTube.